Hey guys, let's continue the conversation on optimal control. So again, in this problem, we're trying to solve a minimization problem or a maximization problem. In this case, well, before we saw a maximization problem, but that typically amounts to, so you want to maximize a function or you can minimize the negative of that function. They equate to the same thing. So namely, we want to in this case, we want to minimize the inputs, okay, for the function, right, p, which is equal to the final value or the final payoff here, plus the cost to go, which is can be written as the integral from 0, close that, t naught to tf of the function L with t, x, and u as arguments, dt. T. Right. So now this payoff function here, phi and plus the integral of L dt, can be subjected to several things. It can be subjected to, when you write that, we say subject to, can be subject to the dynamics of our system, right? So this would be the equations of motion that we want to solve, and then we want to define an input here using this subject to these dynamics. We can also define constraints. We're going to call these as C, with arguments T. Let me turn off my phone. There we go. All right. T, X, and U. So you can have constraints on the time. You can have constraints on the state, on the space, and you can have constraints on the inputs. And we're going to say that these constraints are less than 0. This is the typical way to write it. And then we can also have boundary conditions. So we can set a priori where we want to go and where we start from, and then solve that system of equations here. So again, these are the dynamics. These are the constraints. And this is the boundary conditions. Right. So one way to handle this type of optimization problem, where we have these features, we have a cost function, we have dynamics, constraints, and boundary conditions. We can use what's called Lagrange multipliers. So if we have constraints, dynamics, and a cost function, one approach to find what's called feasible solution, or a solution U that satisfies all of these criteria. One approach is through what's called Lagrange multipliers. And if you were to read textbooks, these could also be called costates or adjoint states. They all mean the same thing. So what we can do with these Lagrange multipliers, so we can embed these constraints in with the dynamics, or in with the cost function. I mean. So we can augment the cost function as the following. So instead of wanting to solve this problem here, we are going to instead solve this problem. So namely the minimization of u in the set of points u, capital U, p, x, t, where that is equal to phi plus nu transpose times h, where again h is the boundary conditions, plus the integral TFL dt plus lambda transpose F plus mu transpose C. Oh, and these are all inside this integral here. Fix that real quick. Move that over. All right. dt. All right, and so then we can also write this as just equal to capital phi plus T naught TF, and then write a calligraph H dt here. Where this calligraph H, yeah, don't go too high. Where this calligraph H here is called a Hamiltonian. All right, so in this case, we have H is equal to L plus lambda transpose F plus mu transpose C. All right. And so there's some necessary conditions called the KKT conditions. We're not going to get into it in this course. However, we can use them and apply them in a linear what's called a linear quadratic program. So these conditions, say the conditions for optimality for a linear quadratic problem are given by. All right, so the first one is come from the state equations. X dot is equal to partial of H partial lambda. Oops. And this transpose. Then we get the costate equations. Lambda dot is equal to minus, let's do this. dH dx partial of H with respect to X transpose. Next one is 3. We have the optimal control condition. All right, and that's partial H with respect to U transpose equal to 0. And then lastly, we get what's called the transversality condition. On the costate. All right, which amounts to a boundary value, a boundary problem, or boundary condition rather, where the final value of lambda is equal to the partial of t with respect to partial of x and the final state. All right, and so next we'll get into finite horizon linear quadratic regular.